Welcome back to Covalent Bonding. This is a big unit, and I've broken it up into chunks on purpose. I don't want to drown you all at once. So take your time, make sure you've mastered videos 1, 2, and 3 before you really get into this one, because this really does build upon each other. What we're going to talk about today is the actual shapes of the molecules. The fact is that everything you've drawn thus far is two-dimensional. When you draw structural formula for water, that's 2 dimensions. Okay, that's not really what the molecule looks like. When you draw methane, okay, carbon tetrahydride, it's 2-dimensional. It's not what the molecules really look like. So what we want to look at today is we want to look at what do these molecules really look like in real life. Now, sometimes it's easy. If there are only 2 atoms, then we know the shape is linear. Okay, because the fact is there is no other possibility. If I have carbon bound to oxygen, okay, even though it's a triple bond, it doesn't matter. There's 2 things. There's one here, there's one here. No matter what, no matter which way you turn it, it is a straight line. But if you have more than 2 atoms, how do I figure out what shape they're in? Okay, what's the angle? How are they bent? How are they arranged? What we're going to use is something called the VSEPR or VSEPR theory. Stands for valence shell electron pair repulsion theory. Wowzers. What it really is saying is that negative electrons are repelling each other. Negative electrons want to be as far apart as they possibly can. They don't want to be together because they have all that negative charge. So we're going to use this theory and we are going to learn about 6 different shapes. Shape number 1 is our linears. Now, I already said linears can be 2 atoms. But, believe it or not, you can also have linear shapes with 3 atoms. What we will see with a linear is we will see 2 atoms coming off the central and no unshared pairs on the central atom. Everything with shape is really dependent on that central atom. I'm not worried about what's happening on the outskirts. I'm worried about the central atom. So if I look at carbon dioxide, okay, there's my carbon dioxide. Yes, there are electrons out here, but I don't care about them. What I care about is this middle one. So there are 2 things coming off the middle one, that oxygen, and there are no unshared pairs on that center. There's no dots left over on that carbon. So what we see here is these electron pairs try to get as far apart from each other as they possibly can. And as far as they can get apart is 180 degrees. If they would bend farther, okay, let's say they'd bend farther down, you can kind of see that what would happen is while they would be farther apart if you're looking at this angle, well, they'd end up being closer together down here. So this kind of back and forth keeps them right at 180 degrees. The only way you will see a linear shape is if you have 2 double bonds or a triple bond. Otherwise, you will have unshared pairs, and the unshared pairs, as we'll talk about later, will affect the shape. The next shape we're going to talk about is called trigonal or triagonal. I've seen it spelled both ways. Trigonal planar or triagonal planar. This is when I have 3 atoms off the central and no unshared pairs. Okay, 3 atoms off the central, no unshared pairs. And again, all we're talking about here is the central atom. Okay, so this is not a normal. All right, this is one of those weirdos we talked about earlier. Think about boron trifluoride. Now, there are, of course, extra electrons around the fluorines. I'm just not putting them on there. But when I have boron trifluoride, I have 3 coming off the center, no unshared pairs. That's not the norm. So my bond angle ends up being 120 degrees. This actually is a planar model because it is in one plane. It is fairly flat. That's the farthest these guys can get. Sometimes you can remember trigonal because it kind of looks like a triangle, and then planar because it also looks like a propeller. If you draw the ball and stick version of this, you can totally see how this looks like a propeller. Okay? Third shape, tetrahedral. Now that tetra ought to clue you in that this is going to be 4. Okay? 4 atoms coming off the central. And again, no unshared pairs. no unshared pairs. So when we do these in 2 dimensions, okay, so if we do carbon tetrafluoride, excuse me, okay, when we look at that, it looks like a big plus sign, and we're like, cool, that makes sense, bond angle at 90 degrees. The problem with this is not 3D, and we have to think in 3D. So if we look at this in 3D, it looks a little different. Again, this is where your PowerPoint will really come in handy, because we all know I can't draw. But in order for this to exist in 3D, we actually don't have a plus sign. What we have is actually a pyramid. Okay, so we've got a pyramid here with a triagonal base. All right, let's see what I can do here. The carbon is in the middle, but it's really the hydrogens that are making the pyramid, and the carbon ends up right smack in the middle. Yes, that's horrendous, but you get the idea. If we look at the ball and stick version, okay, there's the carbon in the middle. You end up with this, okay, like I said, it's a pyramid with a triangular base. Okay, that one's a little better. Not much, but a little bit. But you get the idea. That gives a bond angle of 109.5 degrees. What that means is we're getting these are electron pairs. That's what's happening between these guys. And they've got to get as far away as they possibly can. Again, your PowerPoint is hugely helpful, as are the models that we're making in class. So your tetrahedral, okay, is one of your third shapes. All right, and that's 4 things off the center with no unshared pairs. All right. So now, let's talk about unshared pairs, because everything we've done so far doesn't have any. The thing to consider with unshared pairs is they are still repelling each other. Even though they're not attached, they are still a factor. So let's look at our 4th shape, which is bent. Okay, one of the best examples of a bent molecule is water. You guys learned in biology that water does not look like this. It is not in a straight line. You learned instead that it looks like this. But you probably never learned why. The reason why are these leftover unshared pairs. Okay, they are really still repelling each other. Okay, in fact, they're repelling each other more than these guys are. Because since these are by themselves, okay, there are no positives over here. This hydrogen has positive protons. This hydrogen has positive protons. These guys are nothing. They're all negative. They actually repel each other more than these guys that are bound to hydrogen. So what we see with our bent shape is really another tetrahedral. The oxygen is here, and then the hydrogen is here, okay, 1 hydrogen's here, and then we've got those other unshared pairs. Let me redraw this, get a little better angle. Okay, the unshared pairs are still coming off as part of the shape. So it's still, sorry, that is horrendous. Let me try a ball and stick model. The unshared pairs are still part of the tetrahedral, okay? But it's an atom here, it's an atom here, and then this and this part of the tetrahedral are unshared pairs. So they're still playing a part in the repulsion, but we can't see them. Okay, it's not like it's another atom and another atom, and there's your tetrahedral. Since they're unshared pairs, there's nothing there. And since there's nothing there, what we end up seeing is a bent atom. Okay, so bent atoms, just so you can get this down, have 2 atoms around the center. Okay, 2 atoms coming off the center, and then 1 or 2 unshared pairs. It just kind of depends on which atom we're talking about. Okay, so 1 or 2, sorry, that should have said unshared pairs coming off the central. And again, all we care about is the central. Next shape, same idea, is my pyramidal. Okay, my pyramidal looks, wait for it, like a pyramid. And this is what happens when you have 3 atoms off the center and 1 unshared pair. So ammonia is a great example of this. You look at ammonia, you look at your structural formula, here's what you've got. But the reality is that unshared pair is still repelling. Okay, so that unshared pair, because it's still repelling, again, it's back to that tetrahedral again. Okay, there's a hydrogen, there's a hydrogen, there's a hydrogen. And the unshared pair is up here. You just can't see it. So what you're left with looks like a pyramidal shape. Now I mentioned last time on the bent that repulsion from this unshared pair is actually greater. So in fact, the bond angle on these ends up being slightly less than 109.5 degrees. It's not exactly a tetrahedral. It's slightly more crunched in, if you will. Now you guys do not need to memorize bond angles. I just kind of want to use them to give you an idea. The last shape for us is the big one. Trigonal bipyramidal. Okay, trigonal bipyramidal has 5 atoms coming off the center. Okay, and no unshared pairs. Now you guys know from doing dot diagrams and structural formulas that's not normal. The way to remember it's 5 is look at the prefixes. Trigonal bipyramidal. Now I'm going to try to draw this. I make no promises, but you have a central atom, and I'll even change colors. Coming off the central, one goes straight up, one goes straight down. That's pretty easy. Then there are 3 going around the middle. Okay, yeah, this is horrible, that are all actually at 120 degree angles. Okay, so again, PowerPoint is your friend. There's a great picture on the PowerPoint, but you do have a 90 degree angle here, and then this is actually 120 degrees. That is the farthest apart these guys can all get. And again, it's 5 things coming off the center. This is what we see in the other weirdos, the PCl5. Okay, phosphorus and arsenic are famous for that. So really, all you have to do to determine the shape is 3 things. Number 1, draw the Lewis dot diagram. Okay. Number 2, count the atoms coming off the central. Again, it's all about the central. And count the unshared pairs off the central. Not off the outside, just off that central atom. And then step 3, you just look at your little Vesper theory or Vesper theory to figure out which it is. So the hard part for you guys is you have to memorize it. You have to know if you've got 4 atoms coming off the central and no unshared pairs, that's a tetrahedral. If I have 2 atoms coming off the center and 2 unshared pairs, that's bent. So that's the part you have to memorize, but once you know those 6 shapes, everything else falls into place. Only 2 things left in this chapter. Hang in there.